Hey, what's up everybody? We're going to be talking about counting. As you saw, the fundamental counting rule, and specifically, we're going to be talking about these two questions right here. How many whole numbers are there that have exactly 10 digits and that can be written by using only the numbers 8 and 9? Also, how many whole numbers are there that have at most 10 digits and that can be written by using only the numbers 8 and 9? So let's take a look. First of all, we're trying to write whole numbers. So what's a whole number, right? Like 500, 1000, 1200. Well, we need these whole numbers to have exactly 10 digits and only using the 8 and 9.
Here are a few examples. 8, 9, 8, 9, 8, 9, 9, 8, 9, 8, 9, 8, a bunch of 9, a bunch of 8, things like that.
So that is our task. How many whole numbers are there that have exactly 10 digits? Let's take a look. Here we have 10 positions, and for each of these 10 positions, we have two options because each of these options can be either the number 8 or the number 9. So there's two options for each position. Now there's 10 digits, so 2 times 2 all the way to 2. 10 of those is 2 raised to the 10th power, which is 1024. So that answers our first question. Now, at most, that's tricky. We need to figure out what that means. What does at most 10 digits mean? Let's take this slowly. At most 10 digits means exactly 1 or 2 or 3 or ... all the way to exactly 10 digits. So what's exactly 1? Well, that's 8 or 9. That's a single digit. We know that there's 2 of those. What about exactly 2 digits? 88 is one of those. 80 or 99. That's another one. 89. How about 98? So there's 4 of them. 4 possibilities for that. For exactly 3, you got things like 888, 999. You got 898, 998, etc. You got a bunch of those. It looks like for this one, 2 times 2 times 2, so you got 8 of those. Alright, so it looks like we're adding 2 plus 4 plus 8 all the way to 2 to the 10. And that's what we show right here. For one digit, as we saw, there's 2 possibilities. So that's 2 raised to the 1, or 2. For 2 digits, there's 2 possibilities for the first, 2 possibilities for the second. That's a grand total of 4. Now, we got an or here because we can have, as far as these whole numbers go, with at most 10 digits, that means you could have 1 digit or 2 digits or 3 digits all the way to 10 digits. That's an or, and the or tells us that we should add these numbers. So 2 plus 4 plus 8 all the way to 1024. What is that sum? What if we wanted to add these numbers? Is there an easy way to add these numbers? What's going on with these numbers? They look kind of like there's a pattern here. I want you guys to see that there is a pattern here. What we call that is a geometric sum. Alright, so we are going to have fun exploring a geometric sum right now. So buckle your seatbelts and get ready for the ride. Alright, so check out this cool pattern here. So beautiful. 1 plus 2, 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8. You see what I'm doing? Sort of following a geometric sum. An amazing thing happens here. You see this number 1, and then 3, and then 7, then 15, because look, 1 plus 2 is 3, 1 plus 2 plus 4 is 7. If I add these numbers, I get 15. These numbers are really cool though, because 1, 3, 7, 15, look familiar? They're very close to 2 raised to a number. This is close to 16. This is close to 8. We know that 8 is 2 to the 3rd. This is close to 4. We know that 4 is 2 to the 2nd. So 3 is 4 minus 1. 7 is 8 minus 1. 15 is 16 minus 1. You see that cool pattern? 1 is 2 minus 1. A very beautiful pattern emerging. In fact, if you take the exponent of the biggest term, which is 3, and you add 1, you get 4. So we're kind of thinking there's a pattern here with the geometric sum where 1 plus 2 all the way to 2 to the n is 2 to the n plus 1 minus 1, which is also fascinating because the sum of the digits from like 1 to 4 is 1 less than the next number, which is 8, because 4 plus 2 plus 1 is 7, so it's always 1 less than the next one, right? 1, 2, 4, and 8. If I add those, I get 15, and it's 1 less than the next one, which is 16. So if you add a whole bunch of numbers, 1, 2, 4, 8, 16, 32, if you add, that's a lot of numbers to be adding, but guess what? It's always 1 less than the next one in the geometric sum or in the geometric series. All right, so this is our possible formula for the geometric sum. It's 1 plus r squared all the way to r to the n equals r to the n plus 1 minus 1. Moving on. What if r equals 3? Does this formula always work? Could see 1 plus 3 should be 4. Oh, that's an interesting number, 4. 1 plus 3 plus 9, that's 13. That's interesting. Maybe it's close to 16. Is it? I don't know. What's 3 squared? 9. What's 3 cubed? 27? Maybe it's close to 27. What's 3 squared? 9? I see something with the 9 and a 27 and an 81. But I gotta divide by 2 here. This is harder to see, actually. This one, it gets harder to see as r gets bigger, because now 4 is related to 8 divided by 2, right? That's 9 minus 1. 13 is 26 divided by 2. 40 is 80 divided by 2. So yeah, this one is harder to see, but we see something interesting happening where in the denominator we're getting a 2 now. So where does that 2 come from? Is it 3 minus 1? So maybe this is the formula. So it got a little more complicated, because now we're dividing by r minus 1, whereas in the previous one we didn't divide by anything. With the 2's, things were nice, but maybe we were dividing by 2 minus 1, which is just 1, and that's why we didn't see it. So now we have a division by r minus 1. But does this work for all r's? We can check that with the proof. Here's the proof. We need to prove this thing here. The geometric sum from 1 to r to the n equals to r to the n plus 1 minus 1 divided by r minus 1. Let's see. Here's the official proof. This is a real proof here. If I take the left-hand side and say that equals the left-hand side, I'm trying to show that it equals to the right-hand side. Let's see if it does. So here's the left-hand side. If I multiply it by this, which is really just 1, because you can multiply something by 1. And now here's where it gets interesting. The denominator is r minus 1. I keep that in the denominator. I just shuffle this right into the denominator. And now I multiply 1 times r, and I get r. And I multiply r times r, and I get r squared. If I multiply r squared times r, I get r cubed. If I go all the way down to r to the n times r, I get r to the n plus 1. Okay, so that's the left-hand side. Now, what about the negative 1? If I bring the negative down and I multiply 1 times 1, I get 1. If I multiply r times 1, I get r. R squared times 1, r squared, all the way down to r to the n times 1, that's r to the n. Now, look at how things cancel. That's an r minus an r, they cancel. R squared cancels, r cubed cancels with an r cubed in there. R to the n cancels with that r to the n. The only thing left over
is r to the n plus 1 minus
1. And that, ladies and gentlemen, is what we were trying to prove, which equals to the right-hand side. And we are done. So that's our proof. So this formula does work when starting from 1 on a geometric sum from 1 to r to the n. Now let's use it to get our final sum to answer our question. Remember our question? How many whole numbers are there that have at most 10 digits and that can be written by using only the numbers 8 and 9? Before we found that it was 2 plus 4 plus 8 plus 16 all the way to 1024, which is really this, ending at 2 to the 10. Now the problem is that this starts at 2, and our previous formula, we wanted it to start with 1. So all we got to do is take a 2 out of this. We factor a 2 out. And now we see that this thing stops at 9. So remember, we got to add 1 to that. 9 plus 1 is 10. So there you have it. The 2 is outside factored. And then this, we can use the formula that we just saw. Notice that the denominator is just 1. So all we got to do is plug this into a calculator. Let's do it. So there we have it. 2 times 2 raised to the 10 minus 1 divided by 2 minus 1. And there we have it. 2046. So there are 2046 whole numbers that have at most 10 digits using only the numbers 8 and 9. I hope that helps.
Are the pilots.